Hello, welcome to another edition of our class on mathematical method. In our previous class, we discussed Legendre equation. We solved the equation using the method of Frobenius. We generated the solution to the Legendre equation, and these solutions are called Legendre Polynomial. We also established the relationship between Legendre polynomial of first kind and hypergeometric function. We emphasize the fact that Legendre equation is in Cartesian form. It can be converted to polar form. This was also established. Today's class, we shall be looking at another interesting subtopic under Legendre equation, and that is Legendre polynomial of first kind. Once again, you are welcome. I am Ablegeni Redwanullah in Yoda. We told ourselves in the last class that Legendre polynomial of first kind is denoted and defined by Pn of x equals 1, 3, 5 up to 2n minus 1 divided by n factorial. And then we have x raised to the power n minus n into n minus 1 divided by 2 into 2n minus 1, x raised to the power n minus 2 plus n into n minus 1, n minus 2, n minus 3 divided by 2 multiplied by 4 multiplied by 2n minus 1, 2n minus 3, x raised to the power n minus 4 minus it continues. We established this in the last class. So let us look at, let's call this one equation 1. From this equation, let us generate some Legendre polynomial. Let's start with the first one. P, when n equals to 0, we have P naught of x. And by so doing, what we are going to have here will be 1 divided by is 0 factorial, because our n is 0 factorial. Now, the question now is, do we consider this one as our numerator? The answer is no. What we have here, this denotes first term, second term, the third term, the first term. Our second term will be the product of 1 and 3. The second term is product of 1 and 3, 5. Now, this is a 0th term. How do we generate that? If I multiply the whole of this expression by 1, it does not have any effect. So the one I have at numerator here is this particular one I have used to multiply all. Then the result is x raised to the power 0, and that gives us 1. When n equals to 1, implies that we have this particular one, P1 of x is 1 divided by 1 factorial divided by 1 factorial. Then we have x raised to the power 1, and that gives us x. When n equals to 2, so we have P2 of x equals, that becomes 1 multiplied by 3, 1 multiplied by 3 divided by 2 factorial into, when I have we have this term and this to consider. If you put 2 here, we have x squared minus, put 2 here, 2, 1. We have 2 multiplied by 1 divided by, put 2 at this point. 2 times 2 is 4. 4 minus 1 is 3. We have 2 multiplied by 3. X raised to power 0. So if we expand the whole of this, the final result becomes 1 over 2 into 3x squared minus 1. Following the same line of argument, we can generate more of Legendre polynomial. Let me write up to the 5th one. So our P3 of x, following the same pattern, will have given us 1 over 2, 5x raised to power 3 minus 3x. P4 of x will have given 1 against 8 into 35x raised to power 4 minus 30x squared plus 3. And P5 of x gives 1 against 8, 63 x raised to power 5 minus 70x cubed plus 15x. So you can try the remaining one. Try this one out and try the remaining one so that we see this. Now, one thing that comes to mind is that is it the way we are going to be generating Legendre polynomial? The answer is no. There are still some other easy ways of obtaining Legendre polynomial, which we are going to see as we continue the class. If not today's class, then in our subsequent one we shall see. Let's quickly apply just simple application of what we have written on the board. Let's take example, just one example. Express the polynomial f of x equals 5x squared plus 7x minus x in terms of Legendre, in terms of Legendre polynomials. First up. So let us solve this. It's not difficult. We have x squared, we have x. So what we are going to do is to look at Legendre polynomial and look at those ones that their leading variable is x squared, the leading variable is x, and the last one is a constant. Of course, where we have x squared as leading is in P2. We have our P2 of x to be 1 over 2, 3x squared minus 1. Make x squared subject of formula at this point. We are going to have x squared is 1/3 of 2p2 of x plus 1. However, 1 is another Legendre polynomial, and that gives us 2p2x plus p0 of x. Also, we have established that x is p1 of x. Now, our f of x now, 5x squared plus 7x minus 8 can be written as 5x squared plus 7x minus 8 times 1. This now implies that I have 5. Our x squared is 1/3 2p2 of x plus p0 of x. plus 7. Our x is p1 of x. p1 of x minus 8 multiplied by p0 of x. Expand the brackets. So we are going to have 5 times 2, 10 divided by 3, p2 of x plus 5 over 3. Let's take this one first, plus 7 p1 of x, then 5 divided by 3 minus 8. That is 5 minus 24. Minus 24 against 8, which gives us minus 19 over 8. So this gives minus 19 against 3 rather. Divided by 3 p0 of x. And that is the conversion of the given polynomial to Legendre polynomial of first kind. Another interesting thing about Legendre polynomial is what we refer to as generative function. Function that can be used to generate Legendre polynomial. So let's look at it. Generating function for Pn of x. So let's take the theorem. We'll let Pn of x be Legendre polynomial of first kind. Full stop. The generating function of Pn of x is given as is given as 1 divided by square root of 1 minus 2xt plus t square equals summation n from 0 to infinity Pn of x t raised to power n. That is our generating function for Legendre polynomial of first kind. It's a very useful tool, as we are going to see later in this class. Very powerful tool in discussing some properties of Legendre polynomial of first kind. In fact, so many of properties of Legendre polynomial of first kind will be discussed using the generative function. Since we call this a theorem, in mathematics, theorem is a statement that is very true and required proof. So we are going to look at the proof of this. Proof. So we take the left hand side and move. We start with the left hand side until we arrive at the right hand side. And how do we look at this? The proof is in two forms. Number one, we are going to look at a particular condition that will guarantee the second one. The second one is to expand the whole of this expression using binomial expansion. But before that, there must be condition. This must satisfy before that can actually happen. So let me write the two of them on the board. Number one, we are going to, let me write it this way. The proof is in two forms. One, we need to establish that modulus of 2xt minus t squared is less than 1. Or we call it absolute value. The second one, we expand 1 divided by square root of 1 minus 2xt plus t squared binomially. So that's what we're going to do. So how do we establish the first one? How do we establish the first one? Now to establish that one, let's start this way. Assume that absolute of x is less than or equals to rho, where rho is arbitrary. Also assume that absolute of t is less than square root of 1 plus rho squared minus rho. Then it follows that modulus of 2xt minus t squared, first of all, can be written as modulus of 2xt plus minus t squared. Apply triangle inequality. We have less than or equals to 2xt plus modulus of t squared. Apply some properties of absolute value at this particular point. Of course, we know that under the absolute value, absolute of AB is same thing as absolute of A, absolute of B. So we can, and also that absolute of A squared is same thing as absolute of A all squared. So we can write this one now as equal to absolute of x, absolute of t plus absolute value of t all squared. Now we can now make our substitution. Of course, absolute of x is less than or equals to rho, while absolute of t is less than square root of 1 plus rho square minus rho. So this becomes less than strictly 2 rho. Then we have bracket square root of 1 plus rho squared minus rho. Then if you take the square of this, we have plus bracket 1 plus rho squared plus rho squared minus twice square root of 1 plus rho squared. The whole of this expression, let's see, rho square plus rho square will give us 2 rho square. This multiplied by this cancel out that. Then this multiplying this, sorry, that should be, this is supposed to be minus 2 rho of that. So 2 rho multiplied by this minus 2 rho of that cancels out. So we are left with 1. And therefore, we come to conclusion that 2xt minus t squared is less than 1. So that guaranteed the fact that our left hand side can now be expanded using binomial expansion. So let us now expand that. Let us expand what we have at the right hand side, which is the second part of our proof. Now we can write this one as 1 divided by square root of 1 minus 2xt plus t squared as brackets 1 minus 2xt plus t squared raised to power minus half, which can eventually be written as bracket 1 minus t into 2x plus t minus t everything raised to power minus half. So we can now expand what we have using binomial expansion. By binomial expansion, of course, we know that 1 plus x raised to power n is 1 plus nx plus n into n minus 1 x squared against 2 factorial plus n into n minus 1 n minus 2 x cube divided by 3 factorial plus it continues. Now using these facts at this point, then we are going to generate the following result. Equals 1 plus 1 over 2 t 2x minus t plus 1 multiplied by 3 divided by 2 multiplied by 4 t raised to power 2 2x minus t raised to power 2. Let me take one more term. Plus 1 multiplied by 3 multiplied by 5 divided by 2 multiplied by 4 multiplied by 6 t raised to power 3 into 2x minus t raised to power 3 plus it continues that way. Now what is the major interest? Our major interest is what is going to be the nth power, the coefficient of n power and the nth power itself. Now you look at this, that following this pattern we can come to conclusion that thus the coefficient of t raised to power n in this expansion is 1 multiplied by 3 multiplied by 5. The numerators contain only odd terms, 2n minus 1 divided by the denominator, the even terms, 4, 6. It continues until we have 2n. Then we are going to have 2x raised to power n minus 1/3, 1 multiplied by 3 multiplied by 5 up to 2n minus 3 divided by 2, 4, 6, 2n minus 2, n minus 1 divided by 1 factorial 2x raised to power n minus 2. Let me take one or two more terms under that before we go to the generalization. Plus 1 multiplied by 3 multiplied by 5, 2n minus 5 divided by 2 multiplied by 4 multiplied by 6 up to 2n minus 4, n minus 1, that is n minus 2, n minus 3 divided by 2 factorial into 2x raised to power n minus 4 minus it continues. Now, let us factorize. Let me use the other side. By factorization, the factors here we have 1, 3, 5 up to 2n minus 1 all divided by n factorial into x raised to power n. If you factorize and simplify, we have minus n into n minus 1 divided by 2 into 2n minus 1 plus n minus 1 into n minus 2 n minus 3 divided by 2 multiplied by 4 2n minus 1 2n minus 3 x to the power n minus 4. I have omitted something here. Minus n into n minus 1 divided by 2n minus 1 x raised to power n minus 2. Then minus 1, 2, 3, it continues. So you now see that the whole of this expression defines our Pn of x. Pn of x, let me put it there by definition. So we can now go back to our binomial expansion. We can now go to our binomial expansion. Now, having done this, you will not observe that. Let me quickly remark before generalization here. We find that P1 of x, P2 of x, P3 of x, the least continuum, are coefficients of t squared, t cube, it continues in the expansion. In the expansion of 1 divided by square root of 1 minus 2xt plus t squared. So after that remark, let me rub off this. So thus, 1 divided by square root of 1 minus 2xt plus t squared will now becomes 1 plus t p1 of x plus t squared p2 of x plus it continues until I have t raised to power n pn of x plus it continues, which is now written in compact form as pn of x t raised to power n from 0 to infinity. That is the proof of the generative function of Legendre polynomial of first kind. Let us take another remark here. I have said this earlier on, but let me make it as remark here, since we'll be moving to where we need to apply the generating function. The generating function of Pn of x, which is the Legendre polynomial of first kind, is useful to obtain some properties of Pn of x. Particularly the recurrence relations. So let's now take the recurrence relations. I will list few of them. The list is on and on, depending on the textbook you are using, depending on the number of textbook you have come across, you have read, depends on that. So we can make as many lists as possible. Recurrence relations for Pn of x. Some of the well-known recurrence relation of Pn of x are listed below. 1. Pn plus 1 of x. 2n plus 1 divided by n plus 1 x Pn of x minus n divided by n plus 1 Pn minus 1 of x, provided that n is greater than or equal to 1. Let me quickly say something about the first one. Like I told you earlier on in the class that using the definition of Legendre polynomial of first kind to generate all the needed polynomials may prove a bit tedious. Another useful relation that can help us out in that regard is the number 1. After proving it and proving some of the recurrence relation, I'll go back there and generate the Legendre polynomial using the first relation. But we can only use it provided that our n is greater than or equals to 1. And why is this? If n should be 0, we're going to have issue at this point. This becomes a negative point. So if n is 1, of course, I have 1 here, I have 1 here, then I cannot generate P1 with this formula. So what can be generated from this formula is P2. Because if n is 1, this becomes 2. Then that means that I must have known the value of P0 and P1 before using this formula. So we can generate the Legendre polynomial of first kind from subscript 2 using this formula upward. Sorry, from subscript 2 upward, we can generate the Legendre polynomial using the first relation. Second relation, 2n plus 1. So let me write this one as my second. Mpn of x equals xpn prime of x minus pn minus 1 prime of x. Number 3, 2n plus 1 pn of x equals pn plus 1 prime of x minus pn minus 1 prime of x. Number 4, I have n plus 1 pn of x equals pn plus 1 prime of x minus pn minus 1 prime of x. Number 3 and 4, they look alike, but they are not the same. Look at the right hand side. Something is missing. Pn, yes, something is missing here. X pn prime of x. Yeah. Number 5, I have 1 minus x squared pn prime of x equals n into brackets pn minus 1 of x minus x pn of x. Let's take 6 and 7. Number 6, we have 1 minus x squared, just like we have in number 5, equals n plus 1 into x Pn of x minus Pn plus 1 of x. This simply implies that equation 5 and relation 5 and relation 6 are equivalent. Equation 5 and 6 are equivalent. Then 7. I have 2n plus 1 minus s squared Pn prime of x is the same thing as n into n plus 1 Pn minus 1 of x minus Pn plus 1 of x. So I will make attempt to prove some of them, maybe the first 3, and I leave the remaining one as exercise. So let's look at the first 3, for instance. Proof. For the first one, let us recall our generative function. 1 divided by the square root of minus 2xt plus t squared equals summation Pn of x t raised to power n from 0 to infinity. Now let's quickly differentiate. Let me call this one equation 1. Differentiate equation 1 with respect to t. If we do that, of course, we are going to generate x minus t at numerator divided by square root of 1 minus t plus t squared equals summation n Pn of x t raised to power n minus 1 n from, no, this is raised to power 3 from 0 to infinity. Let me quickly show that. We have that as a 1 minus 2xt plus t squared raised to power minus half. If I differentiate this, we differentiate with respect to power and differentiate what we have inside the bracket. So that becomes minus half into minus 2x plus 2t, everything inside that bracket raised to power minus 3 over 2. So, of course, 2 cancel out and allow the negative to cancel. We have this. Law of indices take its course, then we have this. So, after the differentiation, let us multiply all through by 1 minus 2xt plus t squared, so that we return this one back to its normal shape. Multiply through by 1 minus 2xt plus t squared. If you do that, we have x minus t divided by square root of 2xt plus t squared equals 1 minus 2xt plus t squared summation Pn of x, Pn of x t raised to power n minus 1 from 0 to infinity. That's what we are going to have. So what next? We try as much as possible to expand the bracket. But before that expansion, I can write the left hand side as x minus t summation Pn of x t raised to power n from 0 to infinity. Why? Because if I remove this and put this as 1 and I allow this to be x minus t from here, then I generate what we have here, because this is the definition of the recurrence relation. equals 1 minus 2xt plus t squared summation n from 0 to infinity Pn of x t raised to power n minus 1. Now expansion. Now let us expand the bracket. By expansion, we are going to have x summation Pn of x t raised to power n from 0 to infinity minus summation Pn of x t raised to power n plus 1 is 0 to infinity equals summation nPn of x t raised to power n minus 1 from 0 to infinity minus twice 2x summation n from 0 to infinity n Pn of x t raised to power n plus summation nPn of x t raised to power n plus 1 from 0 to infinity. That's what our expansion on both sides will give. What is the next line of action? You will observe that we have about 4 different powers here, or 3, 1, 2, 3, just 3 different powers. N plus 1, and n minus 1. Those are the power we have. So let us equate the power of t raised to power n on both sides. Equate the power, the coefficient of t raised to power n on both sides. At this side, the coefficient of t raised to power n is xPn of x minus. Now the coefficient of Tn is just a term just before this. That means that the coefficient here will be Pn minus 1 of x equals, we have t raised to power n minus 1. The Tn here is the next term, and the coefficient of the next term will have been n plus 1 Pn plus 1 of x minus 2nx plus a term just before this one is n minus 1. Sorry. Yes, n minus 1. Then we have Pn minus 1 of x. So those are the coefficients of t raised to power n on both sides. So we can now do some simplification. You collect Pn minus 1 together, you make Pn plus 1 subject of formula that gives Pn plus 1 of x equals 2n plus 1 divided by n plus 1 xPn of x minus n divided by n plus 1 Pn minus 1 of x, which is our desirable result. So before I prove the second one, let us quickly look at how we use this one to generate Legendre polynomials. We know that P naught of x, let me just write P naught is 1. We know that P1 is x. Now put n equals to 1 here, we are going to have P2 equals to 3 over 2 x P1 minus 1 over 2 P naught. Substitute for P1 and this. We have 1 over 2 as a common factor. Then x multiply this one gives us 3x squared minus 1. And that's the same thing with what we generated earlier on. P3, I will stop at P3 so that I will not waste much time. simply means that we substitute 2 here, that gives us 5 divided by 3. We have x p2 of x of p2 minus 2 over 3 p1. Of course, 5 over 3x multiplied by 1 over 2 into 3x squared minus 1, which is our p2 that we obtain here, minus 2 over 3x. 3 cancel 3 here. What are we now left with? We are going to have 1 over 2 outside. We have 5x cube minus 5 over 2x minus 2 over 3x. That's what we have. So with this, we can do some fractional work there. 5s cubed minus, that becomes 15 plus 6. 15 plus 4, is it plus 4? 6 is the LCM. Then x is also common. So I factor out this. This is 3 times, that is 15 plus 4. And what do we have? We have 19. Oh, this is 5 over 6, not over 2. 5 over 6. 5 over 6, because 3 cancel 3 here, then 5 over 3 multiplied by half is 5 over 6. So that's what we have. So there is an error here. So this is 6. This is 5 plus 4. And that gives us a 3 over 2x. So that gives us minus 3x, which was the initial value that we obtained. So we can go on and on and on using this relation to generate the Legendre polynomials. So let's take recurrence relation 2. Let us take recurrence relation 2. The recurrence relation 2 is given as npn of x equals xpn prime of x minus pn minus 1 prime of x. So we are to prove this. So let us prove this. We start from our initial step, and that is what we call again 1 divided by square root of 1 minus 2xt plus t squared, the same thing as summation pn of x t raised power n from 0 to infinity. So we differentiate again. Differentiate. With respect to, differentiate what we have here with respect to x. We get the same result with the first relation at this point, t squared equals summation npn of x t raised by n minus 1 from 0 to infinity. Call this equation 1, call this equation 2. Let us also look at derivative with respect to the second variable, which is x. We have differentiated with respect to the first variable t. Let's differentiate again with respect to the second variable, x. If we differentiate with respect to differentiate 1, with respect to x, so we are going to obtain, if I differentiate with respect to x, that is t divided by square root of 1 minus 2xt plus t squared raised to power, sorry, this is going to be raised to power 3, raised to power of 3 equals summation Pn prime of x t raised to power n from 0 to infinity. We call this one equation 3. We did that because in the relation there is a derivative of p. Having done this, we will observe that square root of 1 minus 2xt plus t squared raised to power 3 is common to the two of them. Can we make that one subject of formula? If I make this one subject of formula here, we make it subject of formula there, we now equate, yes. Make square root of 1 minus 2xt plus t squared raised to power 3 the subject of formula. The subject of formula in equation 2 and equation 3. Equation 2 and equation 3. Then equate. Comma, we have. What do we have? If I make this one subject of formula here, I will have then x minus t divided by summation n Pn of x t raised to power n minus 1 from 0 to infinity equals, if I make each subject of formula here, I have it as t divided by summation Pn prime of x t raised to power n from 0 to infinity. So we can now multiply on both ends and see what is going to happen. Let us multiply. Little simplification. We have summation nPn of x t raised to power n from 0 to infinity will give us x summation Pn prime of x n from 0 to infinity t raised to power n minus summation Pn prime of x t raised to power n plus 1 n from 0 to infinity. So equate the coefficient of t raised to power n. At the left hand side, we do not have any problem. The first time at the right hand side, no problem with that one, p prime of x. Then the other term a, t raised to power n, the term just before this particular one is t raised to power n. And that gives us minus Pn minus 1 prime of x, which is the desired, very good property of Legendre polynomial, and that's what we refer to as orthogonal property of Pn of x. orthogonality property of Pn of x. So let's take it as a theorem. Theorem. Suppose we have two Legendre polynomial Pn of x and Pn of x are two Legendre polynomials of the first kind. Then the integral between minus 1 and 1 of Pn of x dx is a conical delta. As a conical delta multiplied by 2 divided by 2n plus 1. Where conical delta is defined as 0 if m is not n, and 1 if m equals to n. So let us establish the proof of this theorem. Let us establish the proof of the theorem. Proof. As seen in the theorem, we are going to divide the proof into two parts. The first part, if m and n are not the same. And the second part, if m and n are the same. If m and n are not the same, we will start from the Legendre equation itself. And if m and n are the same, we are going to make use of the generative function of Legendre. So let's take the first part. Assume m is not n. Recall that a Legendre equation is d dx of 1 minus s squared y prime plus n into n plus 1 y equals to 0. Call this equation 1. Since Pn of x and Pm of x are solutions of 1, comma we have. Since they are solution of 1, so it becomes d dx 1 minus s squared Pn prime of x plus n into n plus 1 Pn of x equals to 0. The second one, the variable will change and become d dx of 1 minus s squared Pn prime of x plus m into n plus 1 Pm of x equals to 0. Call this equation 2 and call this equation 3. Having written equation 2 and equation 3, then what next? What are we going to do from here? We try as much as possible to eliminate Pn here and to eliminate Pn. How do we do that? Multiply equation 2 by Pn and multiply equation 3 by Pn, then subtract the two of them. And let us see what is going to happen. Oh, if we do that, no, there won't be any elimination. The two variables are not the same. This is n, this is n. We will not have any elimination here, but here, can there be any? Yes, there will be elimination at this point. By the time we integrate between minus 1 and 1. I'm sorry for that explanation. There won't be any elimination here. The reason for the multiplication is to eliminate sometimes at this end by the time we integrate between minus 1 and 1. So multiply Pm of x times equation 2 minus Pn of x times equation 3 gives, what are we going to have? We will have ddx of 1 minus s squared Pn prime of x Pm of x minus Pm prime of x Pn of x, then plus n into m plus 1 minus m into m plus 1 into Pn of x and Pm of x. Everything is done. Let us now integrate. Integrating both sides. Integrating both sides from x equals to minus 1 to x equals to 1 gives, now let's look at that. If I integrate both sides, since this is ddx, the integral of this will give the whole of this function. If I substitute minus 1 into this, if I substitute 1 into this expression, I will generate 0. If I substitute minus 1 into this expression, I have 0. Since it is definite integral, 0 minus 0 gives 0. So we are going to be left alone with what we have here. And that means that we now have n squared minus, so that one, rough work, that is n squared minus m squared plus n minus m plus 1. So this gives us n minus m plus 1 and n plus m. N minus m is common. N minus m into n plus m plus 1. Yeah, that is the factorization. So this now implies that I have n minus m, n plus m plus 1 integral minus 1 to 1 of Pn of x Pm of x dx equals 0. Now let's go back to our assumption. We have assumed that m and n are not the same. If m and n are the same, the whole of the left hand side becomes 0. Since they are not the same, that means that the whole of this value is not 0. Divide both sides. Since n is not m, then what now happens? What now happens? From that point, it implies then integral of minus 1 to 1 Pn of x Pm of x dx will automatically become 0. That is the first part of the theorem. Let's now move to the second part of the theorem to establish that. Suppose m is n. So by the generating function, by generating function, comma, 1 over square root of 1 minus 2xt plus t squared will equal to summation Pn of x t raised to power n from 0 to infinity. Also, it will satisfy the second one. 2xt plus t squared will also be summation m from 0 to infinity Pm of x t raised to power n. Call this one, call this 2. Since m and n are the same, let us multiply the two equations and see what the result will look like. So since m equals n, multiply equation 1 by equation 2. What do we have? If I multiply equation 1 by equation 2, I will have summation. Let me take the right hand side, this and this. That becomes Pn of t squared t raised to power 2n, everything equals, we are going to have n from 0 to infinity, everything equals, multiply these two, we are going to have 1 divided by 1 minus 2xt plus t squared. Now integrate both sides. Integrate both sides between x equals minus 1 and x equals to 1. Of course, this one becomes summation n from 0 to infinity. Sorry, this is Pn of x, not t. T raised to power, let me write it this way. Put this one, integral minus 1 to 1, Pn of x squared dx, close it, then t raised to power 2n, everything equals integral minus 1 to 1, 1 over 1 minus 2xt plus t squared dt, dx. Let us integrate the right hand side. Integrate the right hand side. What do we have? If I integrate this, we generate minus 1 over 2t ln 1 minus 2xt plus t squared between minus 1 and 1. That will be our integral. Substitute that value and simplify. Substitute 1 for x, substitute minus 1 for x, simplify. We generate 1 over t, bracket ln 1 plus t minus ln 1 minus t. Expand each of the ln using series. 1 over t into, let us expand this one. Of course, this is 1 minus t plus t squared over 2. Is it 1 minus? No, this is t, sorry. Minus t squared over 2 plus t cube over 3 minus 3 raised to power 4 over 4 plus it continues. Why this one is negative of everything, minus t squared over 2 minus t cube over 3, it continues. So let us subtract. If I subtract, all even times cancel out. We are left with the only odd, all the even powers of t cancels out. This is minus times minus plus, that cancels out and it moves on that way. Then we are going to have this one as 2t plus 2 t raised to power 3 over 3 plus 2 t raised to power 5 over 5 plus it continues. Then what do we do from here? This gives us 2 into 1 plus t squared over 3 plus t raised to power 4 over 5. It continues, which now gives us summation 2 divided by 2n plus 1 t raised to power 2n, n from 0 to infinity. That's what we're going to obtain. Now compare the coefficient of t raised to power 2n. Compare the coefficient of t raised to power 2n implies that we have minus 1 to 1 Pn of x squared dx equals 2 divided by 2n plus 1. So, hence, we can now conclude that integral minus 1 to 1 of Pn of x dx equals 2 divided by 2n plus 1 conical delta mn. Let me write it this way first. Equals 0 if m is not n, equals 2 divided by 2n plus 1 if m is equals to n, which can now be written as 2 divided by 2n plus 1. If you factor out this, multiply this is still 0, and this one will have become 1, which now define conical delta. As an eye opener, suppose we are asked to evaluate integral minus p2 of x and p7 of x dx. Of course, we need not carry out any evaluation here, since 2 and 7 are not the same. We are very sure the result becomes 0. In a similar form, if question asks us minus 1 to 1 p3 of x squared dx, of course here my n is 3. I only need to substitute 3 here. 2 times 3 will give us 6, and the result becomes 2 over 7. So far, we have been discussing polynomial, Legendre polynomial of first kind. We have looked at how to generate polynomial, the Legendre polynomial of first kind, from the general form of that several polynomial can be generated. In the class, we generated the first 3. Also, we look at one powerful tool regarding the Legendre polynomial of first kind, and that is its generating function. We quoted the generating function. We also prove how the generating function was obtained. From the generating function, we prove some recurrence relation, and finally we have looked at orthogonality property of Legendre polynomial. In our next class, we will continue with Legendre polynomial of first kind. Based on orthogonality property and the recurrence relation, I want to take some examples to illustrate what we have done so far in today's class. And after that, we are going to look at another powerful tool as far as Legendre Polynomial of first kind is concerned, which is Rodrich's formula. Till that time that we are going to meet, I wish you all best of luck. Thank you for listening.